lesson about calculus. Chapter 7, Double and Triple Integration. So for the past two lessons, we have proven the volume of the cone using two methods. So those two methods are the first one, disk by disk, whereas for this part basically he wants stacking it up, where for the disk by disk, why didn't we cover this part? Because it is so thin, so basically this is a bigger version, a thicker version. So since it's so thin, we don't count anymore, but there must be a thickness. If not, how many zeros stacked together, it will still be a zero. So it will only approach us to zero. While for the other method that we used was the cylinder by cylinder. But what's so special about the cylinder by cylinder? This cylinder is firstly hollow. Secondly, it don't have these two surfaces. So since it don't have these two surfaces, it's basically saying that from this is very short, and then this part was here, and keep on getting taller until the top part, and then you basically putting one into another like that. Okay. So since it will be like that, it's something more like cutting it straight away like this. Okay. So for this part, and again, they must have a thickness no matter, even if it approaches to zero. Okay. And you might be wondering about how about some other methods? Some other methods like cutting it some other way. Well, we'll be saying about that in some other lessons, okay? Well, for this lesson, what we'll be saying about, so that is the revolving volume for the cone. So for all these over here is the revolving volume that we're talking about now. So for this lesson, we'll be talking about sphere. So spheres, it's also revolving, right? Yes. But wait, what thing is revolving? At first, that there was revolving for the triangle, right? Then what about this? What we gotta see, is this a hollow sphere or is this a solid sphere? Well, for this lesson, we'll be learning for the solid sphere, okay? So now this is solid. So this solid sphere is basically saying the revolving volume of half, basically a semicircle, okay? So for this lesson, we also can have a lot of methods for both hollow spheres and solid spheres. So in this lesson, we'll be solving the solid sphere using the method disk by disk, the same way as how we did it with the cone. It's just that when it is like this, you just have to times 2 of it, okay? So for this part over here, we'll be first doing using this method. Basically, it's supposed to act like this, okay? So what's so special when it is this sphere and the cone? So when it is the cone, you can only do it in the x and y direction, right? While for the sphere, you can do it in all 3 directions, x, y, z, all can. While over here, I only show the x and y, okay? Now over here for this part, let's see it from the front view. So basically you can't see the J anymore. I want to just get half a circle. So as I told you, it's supposed to be a full circle, right? But we only have to take half a circle. Well, for the cone, it's because that it's not two-sided, okay? So for this part, well, it'll be like here, this by this, similarly to the cone. It'll be like, so if you ever want to know more for the cone, you can go back to the past lesson. Basically, it'll be like, And then for here, basically this part is changeable, okay? So for this part over here, what's this length? This length is 1. But what about this length? This length is r, the radius. This length is also r. This length is also r. But here, this part 0. So this from negative r to 0 to r. Okay, like this. Well, what about this thickness? And as I told you over here, since it is so thin, so this we don't count. Well, the thickness, what is it? The thickness is basically dx. Okay, so for this part, what does dv equal to? So dv is equal to all these stacked up together, so it's 2 times of it because it's half the semi-sphere. And then for this part, what will it be? So pi. So this part, what is this length? This length is y as stated. So let me just. So this length, basically y is changeable. So pi y squared dx, like this. Okay. All right. Now over here, what does v equals to? So take the 2 pi out, and then this is from where to where? So where is x going? So x is 0 to r. Y squared dx. So over here for this part, when you need to continue, you can change this y pi to simpler. So for this part, y will become like this. But since over here is capital R for the question, so you use capital R for all these. So it becomes like this, okay? So as for this part, it will become like this, and you can sub it in. So y is equal to this, so y squared is equal to r squared minus x squared. Whereas here will become and then over here, this becomes 2 pi r squared integral from 0 to r dx minus 2 pi integral from 0 to r x squared dx. So it become like this, and then here become 2 pi r square x from 0 to r, and then minus 2 pi. So here is square, so it becomes 2 over 3 pi r square. Well, it's not r square because over here is still x cubed from 0 to r. Then here become 2 pi r cubed minus 2 over 3 pi r cubed. And then here equals to what? Here equals to 4 over 3 pi r cubed. So this is why it's like when you go like this, basically this goes like this. So if it's like this, it's basically this part you tilt it. So it will tilt it basically that. So the second method, where here becomes x, and then this part is like this. Okay. Basically, one is the left and right side like this, and the other one is the top and bottom. So let me just erase this part, okay? Okay, so over here for this part, it will become like this, where it will be 2 pi x squared dy, and v will equal to integral from 0 to here 2 pi and when it's like this, you have x equals to square root r squared minus y squared. So again, this part becomes square, so here will be r squared minus y squared dy, like this, okay? Oops, here is capital. Then for this, once again, same way. Then I'll do that for this part. So it becomes like this, and then for this part here, 2 pi r cubed minus 2 over 3 pi r cubed, and then here equals to 4 over 3 pi r cubed, like this, okay? Alright, so for this part, over here, this is the other method. So if you want another method, you could do it yourself. If you want to do it the last method, whereas the first method was to do it the left and right side. So it becomes like this. Then the second method is, so first method kind of have this plus left and right side. Over here you take half of it, so basically it was the x. Then the other method we used which for this lesson was basically the y like this. And it will be you cut like this in half, and you find the top, then times 2. For the another method you can use is to face the z direction. So if you face the z direction like this, when you have to cut it, you have to cut it like this, okay? So over here, if you're wondering what it could look like, if you make it a bit more obvious, it could look a bit like these two when it's cut disc by disc, okay? So for this lesson, we'll be ending it here. Last but not least, thank you for your watching. So we have solved the volume of a sphere using different methods already, right? So for this lesson, we'll be using another method, whereas it is the shell by shell method. So for this time, the shell by shell method is basically that over here for this part, you open the sphere, and after that inside have more of them, so it's basically somewhat like this, okay? Then over here for this part, over here they are tightly packed together. That over here there won't be any gaps. Like there's no that one. So it's other than it's tightly packed, the her width over here, her for this part need to approach to 0. It need to be as small as possible, because for this part it'll be better if it's approaches to 0 but obviously not completely 0. Then it will be going inside something like this. Okay, so over here for this part is basically what is like for one shell, but the thickness they did not count how thick is it. And for this part, it's just saying that the radius. Okay, so a better way to say it is something like this, where it's like this, and then for this part over here, each time you open it, it will be one more shell, and then here very thin, and then keep on going. So inside each one there's even more. So basically it's somewhere like, and this until the smallest. So until like this. And then for this part over here we still have this and this, and then for the over here for this part, just to get inside have some more. Okay, so for last lesson we have already found out what is the surface area of the sphere. So the surface area is equal to 4 pi r square, right? So over here for this, so let me just rewrite this. So for this part over here, is basically over here it is 4 pi r square. But what so if we find out this? Because then we take the width as approaches to 0. So basically this is the volume for each shell. Okay, each shell. Then for this part over here, so as you keep on going inside until the middle of this part, so you'll be from, so for this part it will be from the most outside over here. So what's this radius? Alright, but you start from the inside, so you start from 0 and then keep on going outside 0 to r like this. Okay, alright, then after that over here each shell is 4 pi r square dr, because that in this case each shell is changeable. It's not a fixed one. This is when it is fixed. It's only the most outside. But this can be until the core also can. So over here for this part, you integrate it, so it's basically a lot of them put together already. And it is feel. So for this part, over here you sub it in. So this is how you get your answer. Okay, so for this part over here, it's not like the this by this or some others that we did it in the past few lessons, because that the past few lessons is only like 2 dimensions, so it can go in front like this, can go upwards, downwards, left, or all those. But this is straight away the whole thing string like this, so there's like no other ways to put it. Okay, so over here for this part is basically, if you can see over here the A and the B, over here is actually different. So it's like, hi, you see the reason why we need this, we need this, the width to be as small as possible is because that if the difference is very big over here for this part, the actual radius will be like 2 of them, because that over here, you see this part has signals already, right? And it's not approaching to 0. So over here, this B and the A, so you instead had like, okay, so although if you stack them together, you'll still get the same volume, but it'll be different from this method because you didn't count the width, because that it approaches to 0, okay? So for this part, we'll be ending it here. So for this lesson, we use the shell by shell method over here. So last but not least, thank you for your watching. But for this lesson, we'll be using a different method, whereas it is triple integration. But wait, normally we do. So let me tell you about the coordinates. So for 2 dimension, basically here like a plane, here like the circle or those it will be, you can use Cartesian coordinate, also known as a rectangular coordinate, or else you can use a polar coordinate, mainly used for circles or this, okay? Well, for 3 dimension, we can use Cartesian coordinate. We also can use spherical coordinate, which is this one, because they're over here the sphere. So for this, we also can use the cylindrical coordinates, like the cylinders, you can use it, okay? So for this part, you'll probably be thinking, wait, then what's all this R about? So let me tell you. So basically, this whole volume of the sphere, this whole sphere is, we have already learned about the shell by shell method, right? So it will be somewhat like this, and then over here is basically one inside another and one inside another, okay? So for this part, this is basically one of the spheres inside it, okay? So this small r is basically the sphere inside it, and then what about this big R? The big R is this big sphere over here, the radius. So that's for the R's. Now for this part over here, so we find one of these small parts like this. So the volume that we are supposed to find is V equals to triple integration dV, right? So this is basically the volume. Then we also can say, so you can either do it like this, was this part of dx, dy, and dz. But nope, we aren't going to use this method this lesson, okay? So for this lesson over here, we'll be having this part, these parts are basically dr, because I realized over here the radius. Then after that, over here, it will be, this part will become ds, and then over here, this green part is for dl, okay? So basically over here, don't get confused with ds and dl. So they are both arcs. So over here, it will become like this. Okay. So for this part, in this case, where is dl? So dl is over here. Okay. Then where's ds? ds will be over here. So basically that it will become something like this. This is what it will look like when you actually do it like this, okay? And then this is basically the part that I'm talking about over here. So this is why you need a triple integration, which will become like this, okay? Alright, so for this part over here, but over here when you need to find this part, what is, okay, dr, you can just put dr, right? Then what about dl and ds? dl, what will it be? And what is ds? So over here for this part, over here, so this is what it will be like. So for this part, you can solve it like this. Then after that, if you realize this arc over here is basically this ds, so what will it be? So for this part over here, it will become, okay, why don't we first draw a line so that we can find it, okay? So become like this, okay? So for this part over here, this is rho. So why can't I just name it some other names? Because at this length it can change, so you obviously won't call it either of the r's. Then wait, then what angle is this? So this angle it is, so over here, you have to imagine, because that this is 3D, so this is basically like, the projection will become from over here down here, so this part will become d theta, okay? Then wait, then what about this angle? So basically this is basically the bit of the extra part, so it is d phi, okay? So wait, but what are these two angles even? Okay, so this phi, okay, so over here, if you're doing physics and math, you'll swap these two around, okay? So for this part, what's this phi in this case? It's the azimuthal angle. Then what about the theta? The theta is the polar angle, okay? So for this part, for ds, whereas it's the one that I said over here, ring by ring. So just wait a moment. Just like this, okay? So for this part, if you want to find this length over here, what method do you use? So this over here, you have a triangle over here, so that is for the, but wait, what is this ds? So ds over here in this case is rho what? Rho d theta over here, okay? And that's how you get the arc. So basically this part, and then here's the length. Okay, so this is just generally, not this, okay? So to find this arc, just call this AB. So arc AB will be equal to R, so over here d theta, or d theta, okay? So for this part will become like this. Then wait, what about DL? So DL over here is another arc. But don't get confused with these two arcs that I told you before, because that this arc over here, instead of being horizontal, because that it is this part, instead this will be vertical. So it will become, so basically now that all these are vertical, so instead of having this row all these, you'll be having, so it will be R, okay? So here will become R, D. So it is was over here, okay? So it will be R, D, phi, like this. But wait a second. Okay, this one, they give you already this part. But wait, what is rho? That's my question. So rho is equals to, so for this part, if you can imagine it over here, there's actually a triangle over here, okay? A right angle triangle. So it will become like this, and then this angle is phi, and then this part is R, and this part is rho. So over here, for this part, rho will equal to R sine phi. Okay, let me just rewrite this. It looks like a P. So like this, okay? So now over here for this part, dl or d phi, then ds, let's just write it in the other way. R sine phi d theta. Then over here dr, you can straight away just write dr. Okay? Alright. So over here for this part, let me just put these together first. Over here will become r square sine phi d phi d theta d r, like this. So over here, which one do you want to do first? This one, this one, this one. Okay, so let's just go for this one first, because over here. So for this part, the R's range, so 0 to R, because I have told you already for this shell by shell, it starts from the 0, basically the middle part, to this bigger sphere over here. So this is only one of them, so that's why this is only small r. So it's until the biggest sphere, so it's somewhere like this one, and then after that over here, so it will be from 0 to r. Then what about theta? So theta, over here, back to this part. So over here for this part, has this angle, it can move the whole 360 degrees, right? So since it can move this whole 360 degrees on this single ring like this, so it will be completely one whole round, which is from 0 to 2 pi. Then what about the d phi? Okay, d phi over here is basically vertically, but if you have realized vertically, it's basically from negative pi to pi, but it will be simpler over here. You can straight away get from 0 to pi, like this, okay? Alright. Wait, maybe I realized there's no such thing like over here. They don't put it together, so perfectly you can do all at the same time. So for this r, 1 over 3 r cubed from 0 to r, then theta, well, it's just a theta, and then from 0 to 2 pi, then times over here. So sine, it will become cosine, right? But wait, over here for this part, it is not cosine, it is negative cosine. And then from 0 to pi. Okay? Alright, now over here it is 1 over 3 r cubed. So pi r. So over here you'll get 2 over 3 pi r cubed. Then times. So over here, if I realize for this part, this is cosine pi is basically negative 1, while this is basically just 0, and then for this part, what you get? Over here, you'll get 2. Okay? Alright. So, over here, 1 to times, it will become 4 over 3 pi r cubed. So, it will be like this and shown. So, this is the answer. So basically for this lesson, we have used the spherical coordinates and the triple integration. So if you're ever wondering about the dx, dy, dz, well, maybe that's for some other time. So basically this part dr is this. So let me just tell you. dr, I forgot to tell you which part dr. dr is basically this, has the thickness over here, okay? So ds and dl I told you already. So for this time we integrate all these three and then sub it in. Well, for the row you can use the this right angle triangle. Well, these two you can simply just find it over here, and this polar angle and the azimuthal angle. Well, for this you just sub them in, and then after that integrate and get the answer. So for this lesson, we'll be ending it here. Last but not least, thank you for your watching. So for this lesson, we'll be using this other method called Jacobian determinant. You also can say Jacobian method of transformation. So for this lesson, we won't be using these parts, but just ignore it, okay? That was what. Okay, so we all know this v is equal to triple integration dv, right? So last lesson we have said about this, right? And yes, this lesson will be using it, so not this ds, dl, and dr. So for this lesson is that, okay, so first of all, we have to find what is the x, y, and z, obviously. But before we do that, I first need to tell you about the Jacobian determinant. So Jacobian determinant is basically over here for this part. X would be equal to x u v w. So this u v w can be any variable, okay? Then y equals to y u v w. Then z will be equal to u v w. So, but over here for this part, does that mean UVW? Does that mean that UVW equals to 1? Because that here J, Y, X, X. So you cancel them, right? If you did that, then you must have you might have mistaken it. So over here, this x, y, z, they are only symbols. Wait, then what about these three? Obviously, coordinates. And so these three, u, v, w is the coordinate for this. So for this part, it's basically just partial x, y, z over partial u, v, w. So it's basically just like this. And then what will it equals to? Yes, over here, partial x, partial u, partial x, partial v, partial x, partial w, partial y, partial y, partial u, partial y, partial v, partial y, partial w, partial z, partial u, partial z, partial v, and partial, okay, it's not 0, it's a partial z, partial w, like this, okay? So this is what it will be like. Now over here for this part, we use so theta, what was it again? The polar angle. And what is phi again? It is so basically for these two angles over here, we'll also be using this over here. So for this part, we'll be using, so here x, y, z, and instead of UVW, because UVW we just do this generally, plus this phi, the azimuthal angle, we'll be using the r, theta, and phi, like this. Then over here for this part, become dr, d theta, d phi. Okay? So now over here for this part, we'll be using d3 instead too. So just wait a moment. Okay. So over here for this part, okay, so for this part, but first of all, what is x actually? What is y actually? What is z actually? So, which one would you find first? Let's see. So actually, the given question wouldn't give you this part first. It will just give you this part only. Okay? So, basically for this part, then you can find z straight away. So, z would be this part, r, then over here, reminder this part is basically the z. And then here is the y, and here is the x, okay? So there won't be any of these low anymore, okay? And here the triangle, this part, it'll be a right angle triangle over here. And you have, so this is basically cosine phi, like this. Then after that, you can project it down until this part and name this angle theta. Then which one can you find already? X. It will become r once again, because over here is, so over here is basically 90 degrees again. Then after that, for this part, sine what? It will become sine phi cosine theta. Okay? Then what about y? You also can find it already. Become a sine phi sine theta. Like this. Okay? Alright. Now over here, for this part we can do it already. So for this part I'm just gonna erase his, wait. So I'm just gonna erase this part, okay? So the partial x over here, it will become this part, and then after that r. So here becomes sine phi cosine theta. Then after that, it will be r cosine phi. So let me just write this a bit cool. Then cosine theta. Then sine sine phi. But over here got negative, okay? Like this, and then other than for this part, the y will become sine phi sine theta. Then after that, r cosine phi then after that over here, cosine phi sine theta, then cosine sine phi cosine theta. Then now for the last one become cosine phi. Then after that, here becomes negative r sine phi. The answer is 0 because that there is the theta is basically just 1. Then after that, over here for this part, you must do like this, 0. Then plus for this part over here, r squared. Then after that, cosine square phi sine phi. Then after that, for this part, cosine square theta. Then after that, over here, it will become plus. Then after that, the next one, over here, negative, negative, positive again. So r square sine square phi. Then after that, it's not sine square phi, it's sine over here one. So sine cube phi and sine square theta. Well, over here, the minus. Let's see. Over here, let's go the opposite way. Oh, there's a negative over here. Becomes plus once again. Then over here becomes r square. And then after that, this part r square sine sine phi, and then after that cosine square phi, and then after that the theta will become sine square theta. Then after that, for the next one, it will become r square sine cube phi. Then after that, cosine square theta, and yeah. Then finally for the last one, once again 0. So this part minus 0. Not minus theta, okay, it's minus 0. Then after that, over here, wait, if you have noticed that these two, you can put them together. And these two, you also can put them together. Well, these two, obviously, you don't care anymore. So, over here will become, wait, but if you still remember, this part become cosine square theta plus sine square theta equals to 1, right? So, for this part, it will be equals to 1. While over here, these two also are square sine phi sine square phi. But wait, why did I write it like this? Is there anything special? Yes, there is. If you check once again, these two can combine once again, and those two parts become 1. So, becomes like this, okay? And now, we're back to normal. So, over here, I'm not gonna erase over here. I'm not gonna write beside, okay? Never mind. Then for the d, I'm gonna do it first, 0 to r. Then what about d theta? D theta in this case, well, okay. For this part, it will become from 0 to 2 pi. Then for the phi, it will become 0 to pi, right? So for this part, over here, if you straight away do it, it will be negative 1 over 3. There's a negative because over here there's sine phi, okay? Then for this part, later I'll tell you why it's a negative over here. 0 to r, then after that, then 2 pi, then times, over here, cosine phi 0 to pi. So now over here, for this part, this sine integration becomes cosine, there will be a negative, okay? That's why there's a negative. Now for this part, if you sub it in, it will become 2. So as it becomes 2, over here becomes, and over here, both are negative, so it becomes positive once again. So it becomes 4 over 3 pi r cube. So this part shown like this, okay? So for this lesson, we have proved the volume of the sphere using the Jacobian determinant, okay? So over here, for this part, we'll be ending it here. Last but not least, thank you for your watching. Now over here, this lesson will be using the triple integration method. But although it says triple integration, we actually also have the Jacobian determinant over here. But there won't be any spherical coordinates. It is polar coordinate. Wait, but you're probably saying that, wait, ain't polar coordinate for 2D planes? How are they used in 3D? Okay, so over here is that this part, this area of the circle. Now this one we can use polar coordinates, right? Yes. So to find this, it will be yep, it's like this, right? Yes. So for this part, what will it equals to? Now over here, for this part, first of all, what is x and what is y? As I told you, we are using the polar coordinates. So x will be equals to, and what y will be equals to? So x, it will be equals to r cosine theta. Well, this is a capital R over here. But later, but the reason, okay, so over here, I can put capital R or small r, but in the end it will all become small r. Later I'll tell why. So I first put capital R according to this. Then this is R sine. Wait, isn't it sine this part? But over here, for this part, this is y and this is x. So you don't need any 90 minus 13, okay? Alright, now over here will be sine x. Okay, so over here is sine theta. I wrote it correctly, okay? But said it wrong. Now over here, for this part, we'll be using the Jacobian's determinant once again. But last lesson, we used the Jacobian determinant with 3 variables. This time we are using 2 variables. So it's basically like x equals to x u v w, y equals to y u v. But over here, there's only 2 variables, so it's only uv. Okay? Alright. So uvw is when it is like, 3 coordinates. Now, over here, once again, it doesn't mean that uv is equal to 1, because this xy is just symbols. Okay? Now, over here, back to this part. So we use the Jacobian's determinant and partial x y over partial u v. But in this case, the uv is basically r and theta, right? And this part you need to add a modulus. Now over here, so that this won't have any negatives. Now over here for this part, partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta, like this. Okay? Alright, now over here, for this part, what will it equals to? So modulus, then after that this part. What is partial x, partial r? So this will become cosine theta, while this part will become negative r sine theta. Then after that, over here, it will be sine theta. Then after that, r cosine theta. And then what will this equals to? So this part minus this part. So it will become So over here there's an identity, whereas if we realize these two have the r, so it becomes cosine square theta plus sine square theta. And what does that equals to? It's equals to 1. So basically this is just equals to r. So all these will become r, d, r, wrong, wait, it's the wrong r, okay. Just wait a moment. So over here will become r d theta, like this, okay? So for this part, over here, what will it become? But first, what's the range? The range over here of this r is from 0 to, okay, so over here for this part, you use capital R over here because over here is capital R. But why not now? Let's relate to this part already. So if we relate to this part, then tell you why is this capital R. The capital R over here is a small r over here. So over here, let's not get confused and we can change it back to this part, okay? So now we change it back to this part. Now the actual capital R is this part. So this is the actual capital R, the radius of the sphere that you are actually finding, and then after that this is just has over here is a disk, and this is a disk that we are using over here, okay? Whereas this part is basically disk by disk. So this, so basically this, each of these disks are basically this thing, okay? So now over here, from 0 to capital R, as this is the actual one. So this is R, this is R. You also can say this one is R, there's a lot. Now over here, what's for theta? 0 to 2 pi over here. Okay, because that can be any degree, and it's 2 pi. Now over here for this part becomes half r square from 0. Wait a second. Okay, so for this part over here, if you realize for this r, so over here from 0 to r, then after that you times 2 pi. Now these two can simplify already. So basically the theta, because it's nothing, so you straight away can sub it in already. Then pi r squared. That's how you get it. So now over here for this part, since we finished with the 2D, so basically now it's the disk by disk already. So basically it's like we have already found this area of this disk. So basically we need to stack them all together. Okay? Alright. So it will be triple integration. This is so specifically the triple integration, polar coordinate and the Jacobian determinant. Now over here for this part, the volume is equal to then dx dy dz. So over here is the triple integration, right? So why not we change this triple integration to an iterated integration, since we have already found out this part. So over here will become, now we can straight away put this part, okay, so over here become 0 to 2 pi, so that's for the theta. So now over here it's a r dr, right? But wait, over here this is just for a disk. So this r over here is actually a small r. Since this is a small r, so we must use a different, so this part is small r, So if you are saying about getting to this area, because that over here you can straight away do over here, but this part you need to change it to row already, because over here we have used a big R already. Now for this part, you will become rho d theta and then dz. But wait, what's the range of z? So the range of this, is small r, not big R. So this range is basically stacked from the bottom until the top. So this is similarly this part is just going down shell by shell, okay? Now over here, since this disk is basically starting from the negative R to R, okay? Because that over here you don't just say 2R, as I'm talking about the coordinates right now. Then after that, over here, you can straight away get this already. But wait a second, how are these two related? Does it mean that this side is wrong? No, it is correct. Let's tell why. Over here, x squared plus y squared is equal to r squared. This small r, because this capital R is actually the small r, okay? So over here, these two Pythagoras theorem become like this. Then what about capital R? It is x squared plus y squared plus z squared equals to capital R squared. Thus x squared plus y squared, so basically r squared, is equal to r squared minus z squared. So this part is basically r squared minus z squared. You can take out the pi already. And now you can do it already. So over here will become r squared z minus 1 over 3 z squared. Z cube because it's a square already. Then after that, from negative r to r. Okay, so over here, now for this part, r squared sub in r become r cube minus this part, but wait, negative and this is only to the power of, so this is just itself, so it becomes negative, so negative positive, so it will become 2r squared minus, well this part, once again, this cube of r is still r cube, while negative, over here, negative r cube is negative r cube. So since it's negative r cube, once again, negative, again positive. So it becomes 2 over 3 z cube. Now over here, I mean by r cube, okay. Now over here, these two minus become 4 over 3 pi r cube. So here proven. Okay, so for this lesson, we have used a bit more methods than last lesson. So actually, if you want to know the difference for last lesson and the lesson before that, actually last lesson's method is more general, because if you have realized, the one that we use, the spherical coordinates, can we use in obviously we can't use it in polar coordinate. But the Jacobian's determinant, at that time we used the 3 variables, whereas over here become 3 times 3, the determinant. While this time we can use it, just that it's 2 times 2 instead. So no matter how many variables, we all can use. So it is more general and more theoretical, okay? Well, for the spherical coordinates, it's just that we used a method that is a bit more convenient, okay? Because if you have realized, is a bit faster using the spherical coordinates. But it's just a special case, whereas it's only for 3 dimensions, whereas Jacobians you can use for no matter how many variables. Now, over here we'll be ending it here. Last but not least, thank you for your watching. So for this lesson, we'll be using cylinder by cylinder, whereas it will become like this. So basically this is like one of the cylinders. It's like this whole sphere. So over here is like, as you can see here, this part and this part, this is a hollow cylinder without these 2 faces, okay? So basically if you want to calculate what is this, it's basically just this part times the height, whereas it is 2 pi r, right? Yes, because that is first of all, it's completely hollow. The thickness approaches to 0 but not actually 0. And then these 2 faces, they are deleted. Okay? So, over here, for this lesson using the cylindrical method, cylinder by cylinder, we basically, at first it's like very long, then after that it becomes shorter and shorter and shorter, while this part will become bigger and bigger and bigger, okay? So, over here, for this part, first of all, we find the volume of one of this. So it will be dV, right? So dV will just be the volume of each one of this, okay? Whereas this, what's the thickness, I'll tell you later. So basically over here it is 2 pi r times how many z? So here is 1z, and because this is the whole thing, so it becomes 2z. And then d what? D, what's the thickness over here? No, don't say dx, dy, it is dr. Okay? Alright, so this r is basically this radius, because this radius can be either x or y, but you can't put x or y. If not, what about the other coordinate? So basically if you write di, is basically he counted at both already. Okay? Alright. And if you wonder about dz, there's no dz over here. Okay? So in order to find v, the volume, you need to integrate it. Right? Yeah, that's what we always do. Then after that, what to do? What is dv? Okay, first, this part you can take out the constant, then after that, r times z, then dr. So over here you can take out the 4 pi integral r z dr. But wait, what's r? The radius can start from 0 basically until capital R. And I told you already, this is like over here is cylinder by cylinder as it gets bigger over here. Okay? Alright, so it's from 0 to capital R. But wait, what about this? We have 2 unknown variables. How are we supposed to solve it? So, over here, for this part, we're going to solve it by... Okay, now, for this part, this is... So what is this part? This part is R. And what is dr? dr is the thickness over here, so it's very, very small, okay? Then after that, over here, if I realize this is R, then wait, what's so special about it? Radius, it can go all like this direction, right? Because this is a sphere, so there's no specific one. But if you draw like, wait a moment. If I realize what is this? This is basically capital R. Have you realized it? So using the Pythagoras theorem, r squared plus z squared is capital R squared, right? So now what is z? Since you use dr, if you change the r, this whole thing will become very complicated. So why don't we just change the z? So what does z equals to? Z squared will equal to r squared minus r squared, right? Now, then what is z? Square root r squared minus r squared. Now over here, it will become r square root r squared minus r squared. Now, can we integrate it already? Yes, we can if you want to make this very complicated. So, an easier way is to put this thing inside, where it will come out a half. Then after that, integral from 0 to capital R, square root r squared minus r squared dr squared. But now that this part is the same, so if you ever wonder why there's no r over here, then you have to use a different method like substitution. So now over here, you can put this inside and these two simplify here too. But over here, this part, r squared, yes, we can count it as a constant right now as it is 1. Then what about this minus? Then you have to put a negative. So this will become negative 2 pi from 0 to r square root r squared minus r squared dr squared minus r squared. Like this. Okay? Alright. Now for this part, finally, we can integrate already because, okay, so now that you just imagine this as one whole thing. Don't do any extra things unless you're doing it like this, whereas now it's not like that. Okay? Alright, now you can ignore this part while r squared. So here it will become r squared minus r squared bracket to the power of 3 over 2. But wait, what do we have the times over here? 2 over 3. Okay? Alright, and then wait, the range is from 0 to r, right? So first of all, here it becomes negative 4 over 3, right? But why not let's sub this in first? So this will become 0. Then minus this part 0. But here got minus, so it becomes plus. 0 sub in 4 over 3 pi r squared. Then after that 3 over 2, right? Wait, but isn't this just like these two times together and then after that these two can simplify and then become 4 over 3 pi r cubed. Proven. Okay, so over here, for this method, for cylinder by cylinder, we basically take this as approaches to 0. So if you don't want this step, you cannot straight away find what is this answer. Okay? Alright, so first you have to find dV. And after you find dV, you can find the volume already by subbing it in. Okay? And sometimes when you have two unknown variables but you only have one of this is d something, try to change the other unknown variable to make it related. So as to make it related, it will become like this. In this case, you can use the Pythagoras theorem. In other case, other methods. Okay? So for this lesson, we're basically doing cylinder by cylinder when that has sort of like stacking up, but they are actually just like putting one inside another over here, like bigger and bigger, and then short. While this thing gets bigger, this will get shorter. So all these put together, one inside another, something like rings together, making a circle, but with a height instead. And then the height becomes shorter as it goes bigger for this part. And you can straight away get the volume of the sphere already. So for this lesson, we'll be ending it here. Last but not least, thank you for your watching. So for this lesson, we'll be using another method to prove the volume of a circle is 4/3 pi r cubed. Well, for this lesson, the method will be by divergence theorem, or you can say as the Gaussian law. Okay, so these two are the same thing, okay? Okay, so over here, I'm going to write down this Gaussian equation over here, and we'll tell you about the parts. So let me first finish writing this part. But wait, over here for this part, is it, okay, first of all, what does this circle over here means when it's like this? So it means that this integration, this surface cannot have like any holes or so. And what does E means? It's the electrostatic field strength. And what's the S? The S is basically the Gaussian surface. Now let me just tell you roughly about what is this graph about. So this big circle is a Gaussian surface. And what's this small circle? The shaded one is basically the charge distribution. And here is supposed to be S, okay? Now, let me explain to you what is this part about. What is the S about? It means this S is basically saying that all of the integration is basically closed whole surface, okay? And now, for the next one. First of all, what is Q? Q is basically the charge. And what does it mean for this whole thing? It just means that it is not continuous, okay? So it can be like, it's just like 1, 2, 3, 4 like that. It don't have like, it's not like over here continuous must be like the whole thing is, you don't have to be continuous, this strict actually. Now over here, what does the epsilon naught mean? Okay, this is not called epsilon 0, this is called epsilon naught. So epsilon naught means, it's basically the permutivity, nope, not the permutation, okay, it's not math, permutivity in vacuum. Because that during in physics, we always use the vacuum. So that you don't have to say about what about the air resistance or those, okay? And it'll be easier. Yeah, after that over here, once again 1 over epsilon naught, triple integration, volume, rho, x, y, z. Then dx, dy, dz. Okay, so this epsilon naught don't need to say anymore. But wait, what is the rho? Don't say that this part is the integrand. Yes, it is this part is the integrand. But what is it for? So this is basically the density. But wait, density of what? Density of water or what? This is the charge density, okay? And what is it? Dx, dy, dz? Needless to say, this is obviously the volume. Okay? Alright. Now over here for this part. Would it be better if this part if you don't have these two parts, won't it be better? So we can say that why not just over here, since both sides have it, so maybe we just do like this. Okay? Alright. But why not we, okay, so first of all, let me just tell you about this dot. This dot is basically, in math, we have the 3 times 4 all those. Those are the numerical multiplication. But in this case, we have the dot product and the cross product. So this is not like the numerical ones. Numerical is just number and number. Here the vector dot vector, what is it? Scalar. Okay? Why not now we call this a different name? So over here, why not let's just call it d vector dot ds vector, like this, and equals to this part. Okay? Alright. Anyways, didn't tell you about one thing? So what is this whole thing? This whole thing, okay, first of all, this is basically the flux through the surface, through the Gaussian surface. And what is this part? Don't care about this, okay? What is this part is the total flux through the Gaussian surface. Okay? Alright. Like this. Okay? So now over here, what can you call this? So this part, let me just tell one thing. What is this? This is equals to, so this is so over here for this part, it will become this. And what is n? N is basically the normal. Oh, so basically this part is the normal, the unit vector, okay? So now that over here we got the ds vector, we can basically put it inside here, okay? And by the way, what is E? So E is basically the electrostatic field strength. Well, over here instead of dotting the ds vector, you can dot the n vector instead. And what is the D? The D is the electrostatic displacement, okay? So wait, what's so special about D vector? D vector is basically, you basically like sub D vector as this one, okay? But what's so special about it? This D vector, because that this D vector has a lot of some other components, whereas we won't be talking about it in this lesson. We'll be specifying about that in the electromagnetic dynamics. And also, this part, what is this? This is basically the Gaussian law. It just said this is for the not continuous, basically the discrete, and this is for the continuous, okay? So over here, this part is basically saying that this one is continuous, okay? Alright, now over here, this is just for charge, right? Why don't we just get it general? So generally, you can write it as A. So this A can be anything, can be charge, can be gravitational, all those. Okay? So this will equal to triple integration. Then after that over here, dv. But wait, what is this thing? This is called del. And what is negative del? Negative del is basically the gradient. Okay? Alright. Now over here, for this part, what is del? Del is basically over here I vector partial x plus j vector partial y plus k vector partial z. Like this. Okay? Alright. Now over here for this part, why not we call it a name? Okay, so over here, why is it general? You don't know what is A. So if here is basically the charge, this part will become, this whole thing will become the charge density. If this is for the gravitational density, then after that, this will become the mass density, okay? So over here, now we just call this a name, whereas we can call it R vector. Then after that, over here, as for this part, it will basically something for sphere. Okay? Alright, now for this part, R vector dot n vector ds will be equal to triple integration over here Oh, whoops. Here it's not plus, here it's just then dot x, y, z. Then after that over here, dv. Okay? So it will be like this. Now what is this? This is basically 3 v dv. So this is basically 3v. Okay, so basically this whole thing is just, wait, this whole thing just has 3 times of this whole volume, right? Yes. And plus another thing is that, where is the divergence theorem? It's basically just this part. Okay? Alright, now over here, we have the dot product. Over here, for this part, what is this scalar? Okay. So over here for this part, let us take A dot B. What is it equals to? I mean A vector dot B vector. Both must have the vector, okay? Then for this part is basically over here. For this part is the A B cosine theta. So this one will become like this, A vector, and what is B vector is basically this part. Okay, so I'm just roughly drawing this. And where is theta? So over here you'll be wondering where is the theta? So this is basically the theta, but how you get like this? So basically it will be something like this. Okay, alright, so over here it will be the AB cosine theta. But wait, what is n? What is this part actually? So this part, it will be 1, okay? So here this n will become 1. Then what about this cosine theta? The cosine theta would be, the theta would be 0. But what is cosine 0? 1 again. So perfectly over here is basically just r. Like this, okay? Alright, so now over here for this part, why don't we change this to r cubed and then ds over r squared. Now what is ds over r squared? What's so special about it? ds over r squared, it will be d omega. So wait, what is this d omega? So this is basically the solid angle. And what is the solid angle? Over here it will be 4 pi. Okay? But wait, over here 4 pi, that's only for the solid angle. What about this r cube? Yes, there will also be this r cube. Okay? Now, back to this part. So these two are same, right? These are same. So basically 3v is equals 4 pi r cubed. So what is v? V is 4 over 3 pi r cubed, and here shown. Now over here we have proven what is v. So over here we use both of these, okay? So the Gaussian law we use it at first over here. Then after that we don't use this part, as this sphere is obviously continuous. This sphere couldn't have holes, if not it wouldn't be a sphere anymore, right? Then so we use these two parts, and after we use these two parts, we can make it turn into the general form. Over here we find the del, then the del over, so basically the del is just like this, okay? So if we want to know for this part, is basically we have learned it in the partial differential equations. Then after that we just put this a as this r over here. Then after that, for this part, we use both over here and straight away solving it using the dot product. So when we straight away solve it the dot product, we get this. And then when we solve using this triple integration, we get 3v. So since these two all come from the same question over here, so basically these two are equal. And once these two are equal, you can find what is the volume already. So for this lesson, so over here, let me just show you what is it like. Okay, so just take a quick look. Okay, so we'll be ending it here. Last but not least, thank you for your watching. So for this lesson, we'll be once again proving the volume of a sphere. So we have used 7 methods to prove the volume of the sphere already. So for this lesson, we'll be using the Cavalieri's principle. Wait, at the first place, what is the Cavalieri's principle? So you see these two figures over here? Okay, so why don't we just take this figure as this part? So what it actually is just that over here, it needs these two surfaces need to be the same, and then the height and the cross section, all these need to be the same. So let me show you an example of it. So for this part over here, we have one stack over here, and then after that we have another stack over here for this part. So over here for this, no matter what shape is it, so for this part, let's take that you slant over here. But first, we need to assume something. We need to assume that this surface is equal to this surface. Okay? Alright, so we need to first assume that these two surfaces are the same. And then the number, so this thickness of these two also same. And then the number of these stacked together also the same. So basically that the height is the same. Okay? Alright. Now that the height is the same, over here we slant it for this part. Wait a moment. So over here slant it. Then after that, like this. So slant it like this, okay? Then for the circle, you also slant it. So the circle, it become like this. Okay, so although these two might be different shape, but since the height are the same and the cross section, they are also the same over here, and the surface for this part are also the same. Actually, these two are basically the same thing. Okay, if you want to try another more obvious example, you can use like coins, stack them together, and then like this, stand different sides. They are still the same volume, right? Yes, they are still the same volume. So the Cavalieri's principle is basically that they can be different shape, but for this part, no matter how much they're slanted, if their height are the same, their cross section are the same, and all these surfaces are the same, then these two volumes are definitely the same. Okay? Alright. So over here, for this part, I have told you about the Cavalieri's principle. Now back to the question. Over here, you need to prove for the sphere, right? So, but how are you even supposed to prove for the sphere? So what if we just take half of the sphere? So basically it's a semi-sphere. So this semi-sphere, you actually can call it a lot of names. So in English you can either call it semi-sphere, hemisphere, while in French you can say as semi-sphere. I mean by demi-sphere. Then after that, in other languages like Japanese, you can say hankyu and some other languages. Okay? So for this part, for this semi-sphere over here, you can, so over here this is just the model of the semi-sphere. For this part, okay, so here is, oh yes, it's just the radius, right? And then for this, the x is basically for this part, as over here the r that's changeable. And then over here, you have a cylinder. Okay, so before we check on this one, why don't we say for this, why don't we just put a cone inside it? So a cone basically somewhat like this, but a bit more flatter and bigger. And then you put it inside this cone. and this part needs to perfectly fit over here, and then the height straight away touches, okay? So it will be somewhat like this. Then what about for this part? Okay, so let's take a cylinder that this cone actually also can fit in it. So now that you get this cone over here, but firstly, if you see over here for this part, so let's take this over here. This part is R, right? And this part, what angle is this? Okay, so for any the semi-sphere, it will touch the middle part of this, and these will touch this part. Then this is basically a right angle. Okay, so let me just change the marker. Okay, so this will become a right angle, right? And adding to that these two actually it's split from the middle. So over here, actually these two are the same length. So this is basically an isosceles triangle. Okay, all right. But what's so special about this isosceles triangle? This is a right isosceles triangle. So over here, now for this part, if I realize over here, this is also right angles. Okay, and over here, these two angles will be 45 degrees. Okay, so since they are 45 degrees, yes, it's true that these two are basically just isosceles triangles. And getting back to this part, over here we will call this part X. So this whole thing will become R, right? And this part R, right? So this is this isosceles triangle, and now we take the height as X and base as X, because that for this part 90 degrees, 45 degrees, 45 degrees. And this part X, once again, 45 degrees, then over here got 90 degrees, and this part, if we draw this line over here, it will also be 45 degrees, right? So this is X, these two are actually similar. So these two are similar, so over here is X, here is also X. So now that here is also X, you basically know that these two are actually just equal. And over here, for this part, let us take that these two parts are the same, okay? So these two parts, we just made them the same, so these are both X. And what about this R? What would this R be? So over here for this part, let's just take this disk out, and then for this part, the part and the green part is basically this big circle over here. So this, what is this big circle over here? This is basically this whole cylinder, one small hot disk for this part, whereas it's basically that you cut open this part and what it would look like. And then for this part, this whole thing is this whole cylinder over here, and then this part would be this X over here. So now that this is X, actually this part is also X. Okay, so actually this part is this part. Okay, and another thing is that if you realize over here for this part, another thing you can get to this is that for this, do you see any relation between the X, R and this R? This is basically the Pythagoras theorem, whereas R squared is equal to small r squared is equals to capital R squared minus X squared. So if you are wondering why is it like this, you first ignore the pi, then you realize why is it like this. And now so if you realize this small the small pi r squared over here is basically just this whole thing minus this part. Okay, so basically this whole big circle minus this small circle will become this thing that you can be like the ring. Okay, so it will somewhat be like the So somehow this would be like the r over here, the small r for this part, and then after that, this is the x for this part, and then over here, where is the capital R basically is basically until this end, okay? Then where is, so what is the small r, the small pi r square? It's basically this shaded part between these two. So this part is perfectly equals to these two, this whole thing. So basically just this layer, okay? Just for this layer. So now that over here, wait, so if you have realized, if it is like this, and when this goes down, this also is like this, then for this part, isn't it just like this whole cylinder is basically this cone and this semi-sphere together? Yes, it is. Because perfectly, if I realize it over here, for every layer, they are all the same. They are perfectly like, you know, the same, right? How you be like, if you try from the top to the end, they are always, this pi r square is equal to this part, okay? So this is by using the Pythagoras theorem, and this part, you add a pi over here, and you realize, and if you see from this part, you realize that for each of this layer, this pi small r square is basically this pi capital R square minus this pi x square, okay? So what is the volume of a semisphere? The volume of the semisphere is basically just the volume of the cylinder minus the volume of this cone. And this will become the volume of the semisphere. And similarly, if this part is semisphere, the part over here will become, this part will become the volume of the cone, okay? So it's basically just like this cone and this semisphere together will make up this cylinder. So this part, okay, we can find the volume of the cylinder and the volume of the cone, right? So what's the volume of the cylinder? It's basically pi r square, or okay, so here it's pi r square, right, times the height. The height is also r, so it becomes pi r cubed. Then what about the cone? The cone is basically minus this part. The volume of a cone is 1 over 3 pi r square times the height. But the height is also r, so it becomes 1 over 3 pi r cubed. Then this will be equal to 2 over 3 pi r cubed. But wait, this is only the one. Whoops, it's not square. But wait a second, isn't this just the semisphere? This is not the whole sphere. So what is the volume of the actual sphere? It is 4 over 3 pi r cubed. Okay, so this is shown. Okay, so that is why at the start I told you that this can be the easiest, also can be the hardest. So for this part over here, it's basically that you have to understand that this volume of a sphere is basically the volume of the cone over here with the same base and the height, the same height, and the cone with the same base and the same height. And when they minus, they are basically the volume of the semisphere. Okay. So over here, if we just check the working only, you realize that over here it's only like a few steps, and you minus and times 2, and that's it. But sometimes when we try to understand why does this perfectly becomes like this. This is why we arrowed here. Why is it perfectly like this? You might not be able to understand. So it's basically about the Calvary's principle, okay? So for this lesson, we'll be ending it here. Last but not least, thank you for your watching.